Okay, so this is our last talk before the afternoon break here on the Saturday of North Bay Python 2023. And our next talk I'm very pleased about as a maintainer of the PANTS project who look after PEX itself, that we've got somebody who's not involved in the PANTS project here to talk about how excellent PEX is. Please welcome Shalabh Chaturvedi.
Hi everyone, my name is Shalabh and I'm going to be talking about deploying your code faster and also about this tool called PEX. So it's a two-in-one talk, like a two for the price of one. Here's the structure of my talk. First, before I get into PEX, I'm going to give you some background context and describe the problem, and then go on to the solution, which includes PEX, and finally, some bonus content. So here's the context. I work on Dagster Cloud. Dagster is a product you use to build and run data pipelines. And it looks like this. You write some Python code that's on the left to define your data pipeline. And then you have a web UI, which you could use to visualize the pipeline, run the pipeline, inspect the status, and so on. And this is a pretty simple pipeline. It only has two, what we call them, data assets. And you can kind of see the two functions in the code and the two boxes in the UI. But you can imagine these things can get pretty large. Data engineers use data pipelines to manage hundreds, even thousands of tables in their warehouse. They run all kinds of business analytics, train machine learning models, and so on. So back to this example. You'll notice it's a screenshot, and it's of my laptop. And so the entire thing can run locally. And when you're working locally, you could edit the code, refresh your web UI, just rerun your change, see how it works out, and local development works great. This picture, however, changes in Dagster Cloud. So in Dagster Cloud, we have a product called serverless, where you don't need to run Dagster at all. And it works like this. Now, you still write the Python code to define your pipeline, but then you commit it to GitHub or GitLab, and then a CI/CD workflow runs in GitHub and builds and deploys your code to Dagster Cloud. The web UI now lives in Dagster Cloud. And when you run a pipeline, it also runs in the cloud. And you'd want to do this for many reasons. You may have production pipelines you don't want to run on your laptop. You have, you just want to try out Dagster, but you don't want to install it locally. You just want to play with the cloud, and you're afraid of Python dependencies, so you don't want to install it locally. Or you are using one of these shared cloud environments. So we have this feature called branch deployments. And the way it works is you have your pipeline code, and for every Git branch you create with a PR, we create a separate instance of the pipeline in cloud. And you can interact with that pipeline, with that branch pipeline. It's mainly for testing your change before you land it. And you could run that pipeline. Typically, people set it up to run like against a staging database. Sometimes they even set it up to run against like a lightweight clone or branch of the database, when databases support that. So let's actually look at what happens when the code is deployed from like a CI/CD system to cloud. So when we built this initially, we just copied the existing pattern for Dagster production deployments. And what happens in CI is we take your code, build a Docker image, and push it. And in our cloud, we provision a new container, download the Docker image, and run it. Very typical process. The only problem was that the entire build and deploy process took like 3 to 5 minutes. So now, if you occasionally push to production and are used to waiting, it's not a big deal. But if you're like in interactive, iterative development using one of those shared environments, or for any other reason, or maybe you push to production like very often, which is fine, then like waiting 3 to 5 minutes is not great. It's really slow development cycle. And developer experience is like one of our key design philosophies. So we do care about developers. Developers. That's one of our stated values. So we wanted to make this process faster. And we profiled it. And this is what we found. Most of the time spent is in those bottom 2 boxes. So the first is 60 seconds to build and upload a Docker image, and 90 seconds to run the Docker image in AWS. So not a big surprise. And that 180 seconds is really the lower bound. If you have larger images or if AWS takes longer, this goes up. Now, we thought we could deal with that. We can make it faster, because let's think about what happens if you make a change. So say you make a small change in your code. You just change one doc string, and that doc string shows up in the UI, so you commit it, and it should show up in the UI. Even for that one change, we do the entire build and deploy process. So we build a new Docker image in cloud. We'll spin up a new container. We'll throw away the old container. Even though both the images are mostly identical, there's very little difference between them. So we thought, yeah, we'll figure out a way to speed up Docker. And based on the profile, this is the way we approached the problem first. We said, we need a way to speed up Docker builds, and we need a way to speed up container deploys. Now, we did some research, and I'd like to share some fun facts about both of these steps that we learned in that research. So let's talk about Docker builds. Imagine you have a Docker image built and published. So it's sitting in a registry somewhere. And you want to publish a new version of that Docker image. And all you want to change is you want to add like one small file to that image. So you have a bunch of layers in the registry somewhere, and you want to like slip in one extra layer at the bottom. Now layers are how Docker images are structured internally. Each layer is basically a Docker image is a stack of layers. And each layer is a set of files, and each layer also has its own hash. And these are stored independently in the registry. So the best outcome here would be the existing layers don't go anywhere, but then you have a new layer show up at the very end, and the new image is basically all of the existing layers plus one new layer. Now, if you want to make this happen, you can't. Or at least you can't make this happen easily. Because to add a file, typically you'd add it to your Docker file, right? And then even if you add it at the very bottom, you have your new Docker file, you give it to GitHub to build, and then what happens? GitHub will basically rebuild the whole thing, top to bottom, execute it line by line, pull the base image, install the dependencies, everything, and at the end it'll put in the new file. Now here's another thing. If while rebuilding the image, GitHub creates layers identical to layers that already exist in the registry, right? These layers will still have new image hashes. Now this is the non-deterministic thing I'm going to talk about in a bit. But basically, at the end, you end up with a whole bunch of new layers, and which might get pushed. So Docker, however, does have a build cache, which makes sense to enable. So let's say we do that. We've enabled the build cache, and we rebuild this image with this one new file. Then what happens? Well, now the build process will go through the Docker file. At some point, it will say, oh, this is a layer that's already present. I don't need to rebuild it. And that's great. But the next thing it does is it downloads that layer from the cache machine onto the build machine. And that's because all of these layers need to be present on the build machine. And so you have hundreds of megabytes that being downloaded from cache machine to build machine of layers that are not going to be changed. These layers are like not modified with the new build process. So that's what I mean by not fully incremental. The second point here, not deterministic, this was more of a surprise for me, but I say surprise is more like a shocker when I found that Docker builds are not deterministic. And you can easily try this out on your laptop as well. So what you can do is, if you build the same Docker image 2 times on the same machine with the same set of input files, you will end up with 2 Docker images. But you do one thing. You blow away your local cache between those 2 builds completely, right? System prune -a or whatever. What will happen is you'll have 2 distinct Docker hashes, Docker shards. They'll be different ones. Why is that? The Docker images have the same exact files. Well, I don't know why that happens, honestly, but somebody told me it has to do with these timestamps in the file system. Anyway, what was clear here was that to really speed up the Docker build, we'd have to do something like spin up our own build infra with our own machines, where we can have a long-lived sort of persistent disk cache, and maybe use some combination of even going around the build system and poking directly at the registry, the layer API, and updating stuff there. So some serious work would be required. OK, let's talk about container deploys. For running our system in cloud, we use AWS Fargate. It is an on-demand container service. So you don't have to plan ahead. You can just ask Fargate, I want a container with these specs, and here's an image to run on it, and it will spin it up for you. That's great. The only thing is, however, that it takes at least 45 seconds to spin up a new image, often 60 seconds or longer. And it also, one of the reasons that is that it doesn't let you do any image layer caching. So every time you deploy a new container, it pulls the image from the registry. There's no local cache present. You can see like a bug that's open for 3 years for image caching for Fargate. It has collected, you probably can't read, 128 comments from January 2020. This bug's still open. So the solution here would be to switch to another computer environment. We could switch to something like EC2, also from AWS, but then we'd have to do extra work. We'd have to plan ahead of like how do we size our cluster, because essentially we would pre-provision a bunch of machines or a bunch of VMs and then use it to run to provision containers. So we'd have to plan how we scale it. We'd have to monitor it. Figure out how to handle spikes that are larger than what our cluster can accommodate. So it is possible, but just a lot more operational work. And even if we do that, it's not clear what is really the lower bound of a Docker container launch, because you are going to, in the end, pull a full image and boot it up. So we started thinking about other options. And this is where we took a step back and kind of reframed the problem and thought about it not as a problem of speeding up Docker builds, but as a problem of synchronizing a user environment with a cloud environment. So the idea is the user specifies an environment, and their code is part of that environment, and we replicate that environment in the cloud. And as the user makes changes to their environment, we propagate those changes to our replica, right? So it's synchronization, and it's like one-way synchronization. There's many ways to sort of model synchronization, like what are the actual, how do you model an environment? Is it a set of files? Is it something else? And how do you synchronize them? This is the pattern. This is the model we chose. So I'm going to go right to left on this equation. An environment consists of 3 parts. The user gives us some code they want to run. That's the first part. Their code, this Python code, includes some dependencies. That's the second part. And to run everything, we need a Python interpreter and an operating system. So that's the third part, the base. And what we wanted was a system where We only have to update the parts that changed. So if only the user code changes, but the dependencies and the Python version, whatever, did not change, we don't want to build and deploy the base and dependencies. We only want to deploy the code. And to do this, we looked at all various tools that are out there. And one tool looked really promising. Anybody want to guess? That's right. Nobody said it. PEX. So before I get into how PEX fits into this model, I'm going to talk a little more. I'm just going to talk about PEX. What is PEX? PEX is one of the tools that's part of a larger project called Pants Build. You can use PEX without using Pants, and PEX is a build tool. You give it a set of Python packages, and it creates a file containing those packages. So here's an example. Here I run PEX with and pass it Dagster and Pandas. Both are packages available on PyPI, and ask it to create this file called out.pex. And the files produced by the PEX tool are also called PEX files, by the way. So this out.pex has many interesting properties. We'll go over them. The first one you can see here is that it is an executable file. You can run it. And when you run it, it behaves like a Python interpreter. In this Python environment, I have the two packages that I specified. The packages specified Dagster and Pandas are available, and I can actually import them. What this means is that PEX included not just those two packages, but also the entire set of transitive dependencies for those packages. And that's why the imports work. Now, another thing about the PEX files are that they're zip files, so you can actually unzip them, look at what's inside. Very convenient, easy to inspect. PEX environments are isolated. The environment produced by a PEX file is completely isolated from the system environment. So here I install Pandas into my system, and then I install PEX, and then I install Dagster into a PEX file. And then when I run the PEX file, Dagster is available, but importantly, Pandas is not. PEX files are composable. Here, I create two separate PEX files, one with just Dagster, one with just Pandas. And I could run them independently, but using this variable called PEX path, I can combine both environments, both of those files, into a single environment. Remember I said Docker builds are not deterministic. Well, PEX builds are. So if you have two PEX files with the exact same set of Python dependencies, same versions, same platform, those two files will be bit for bit identical. You could create them at separate times, but if it has the same set of dependencies, you'll have the same exact file. So I've been showing you examples where I first build a PEX, and then I run the PEX right away, so it's on the same machine, which means the same Python interpreter is available during the build and the run. The question is, can you build a PEX that runs on a different platform? And yes, you can, with some limitations. You can build a PEX for any platform, either a different interpreter on the same OS or even a different OS, as long as all of the dependencies you want included are available as binary wheels or as pure Python packages. So if you have a source distribution with some C code that needs to be compiled for a target platform, well, PEX will not cross-compile it for you. OK, so back to our equation. Our environment has three parts. How do we model this with PEX? This is what we do. The operating system and the Python interpreter are part of a Docker image. So that's the base Docker image. One PEX file, here deps.pex, contains all of the user dependencies, all of the Python dependencies for the user. And another PEX file, source.pex, contains all of the user code. This is how it works. I'll go through three separate cases here and describe, like, this is again back to the build and deploy process. What happens in the CI system and what happens in our cloud. So imagine you have a brand new deployment, and what we do in CI is we build the dependencies PEX, we build the code PEX, and we upload them to S3. Okay? And then what we do in our cloud is we spin up a new container using a standard pre-built Python image. So we're not taking an image from a user now. It's just a standard pre-built image. We download those PEX files on the container, and we can combine them to create a combined environment. And now we have our three layers. We've got the base, we've got the dependencies, and we've got the source. Imagine you make some change to your code, and you need some change to a dependency, and you commit that change. So in CI, we still need to build both PEXs, because we need to rebuild the dependencies, and we need to build the source, and we upload it. In cloud, however, it's a little different. We don't spin up a new container. We use the same warm container. We just download the new files onto the existing container and run them. And because PEX has isolation, we don't have to worry about what existing PEX was already there and where it was running. The new one is basically going to be a new environment. Now, finally, for a fast build, imagine you only change your source. Here, we only need to build a source PEX and upload it. And then we again run it on the same container. This time we use the dependencies PEX from the previous run. And we can again create a combined environment. So we've got a full build first where we have to build everything. And the fast build is the sort of other end of the spectrum where only the source code changes. So you'll notice for all three cases, we don't do a Docker build at all. There is no Docker build involved. And only for 2 out of 3 cases, or 1 out of 3 cases, we need to spin up a new container if it's a new deployment. Otherwise, we just reuse the container. So another thing we've done is the user doesn't need to change their code at all. We scan their requirements text or setup.py to determine if the dependencies have changed. So anyway, let's look at those graphs again. Now, fast build is really fast. So it's showing 35 seconds here, the full deploy time, of which 10 seconds are just to spin up a GitHub runner. But all fast builds are doing is zipping up some Python code that's already present on the build machine, uploading it to S3, and the rest of the time is sort of us finding it, downloading it, and running it. A full build is still faster than a full Docker deploy we were doing. And that's because we omit it's slightly faster. That's because we don't do the Docker build anymore. So compared to our original deploy step, where we had no fast path at all, our fast path here is 5 times faster. 5 times. And we've seen users use this very effectively. These are screenshots of our deploy log from our cloud setup. And in the center column here, you can see how long the deploy took. If you can't read it, it's around 20 seconds, 20, 19, 18, and so on. And each screenshot is from one user. So on the left, you can kind of see a bunch of deploys happening in quick succession. It appears to be an iterative development process going on there. Something like that would be fairly painful if you had to wait. Imagine waiting 5 minutes for every time you commit your code and wait for the UI to update. So on the left here, you can see you can even catch errors quickly. So there's a fast failure, the red bar there. And then this person's able to fix it quickly with a couple of fast follow-ups. This repeatability is a design constraint I haven't talked about yet. But imagine you build and upload a pipeline. Typically, you run it many times because it might be running on a schedule, or for whatever reason, you've built a pipeline, you run it many times. And so we want to run the exact same snapshot of the code every time. The way we used to do this is just identify what runs with the Docker tag. So every time we use the same Docker image if we ever want to run it. With PEX, we use a PEX tag in addition to the Docker tag. So the Docker tag specifies like which base image is used, and the PEX tag is something we build from just the file names of the PEX files we have. And I was showing earlier file names like deps.pex and source.pex. We don't actually use those short file names. We put the hash of the file in the file name itself, so it's content addressed. There are limitations with this approach. So PEX gives you a nice isolated in Python environments, but does not give you any CPU isolation. There's no RAM isolation. They're just processes in the same environment. We thought about like running multiple deployments from the same user in the same container, but we realized like they could easily step on each other. One could use a lot of memory, slow the other one down, maybe even kill another deployment. So you still need sort of where you need container level isolation for CPU and memory, you still need those containers. And if you use a system, any sort of cloud compute environment, like Fargate or basically ECS, they have this abstraction typically called a service, where if your container dies for whatever reason, goes out of memory or anything, it automatically creates a replacement and spins that up for you. With PEX, it needs a little more work to get the same fault tolerance, because now we need something watching. It's not a container level failure anymore. It's a process level failure. So we need something watching the process, and then it needs to decide what to do if it fails. So cross builds are an issue for us because, well, users could deploy directly from their, let's say, Mac laptop into cloud. And our cloud runs Linux, so the PEX files we need should be compatible with the version of Linux we run in our cloud. And as we know, like cross builds are a little tricky. Building those on a Mac is not always possible. If your PEX files only have Python code, or you always have the wheels, it'll work. But if in your set of transitive dependencies, you like hit one source package with some C code in there that needs to be compiled, PEX cannot cross-compile that for you. The way we solve this is actually using a Docker builder container on the Mac. And this is not a problem for Docker builds at all anyway, because if you're building a Linux Docker image on a Mac, a Linux container will be running on your build machine, on your Mac. And so you can do Linux compilation on there. That's probably why it needs all of the layers present at build time. However, yeah, so we saw this, there's a flag. You can ask our tool to spin up do the build in a Docker container, if it fails to build outside of it. And this is also not a problem with GitHub or GitLab, because they're already Linux. So we just pick a version of the runner that is compatible with our cloud. Okay. Is it time? Okay. Well, I think I took a fair bit longer than I expected. I am going to skip over. Just give you one thing you can use with PEX. Instead of using virtual environments that are to try out new packages, you can use PEX, and it'll create a sort of ad hoc throwaway virtual environment. So you don't have to keep downloading packages and figure out where to put them and end up with a lot of clutter. That happens to me, but now I just use PEX. And finally, you can also if you have a tool you want to distribute, you could build it as a PEX file. You don't need to always ship it as a Python package. It makes it easier if your users can just download and run a file sometimes, and they don't want to deal with Python dependencies. So anyway, the last thing I'll leave you with is a thought. Reframe problems often, because if you reframe a problem, thinking of a Docker build versus thinking of solving the problem of synchronized environments, we come up with different kinds of solutions, and sort of what is fair game is different. What kind of solutions we deem acceptable are different. And I feel we don't do this often enough. So you may not always come up with a better solution or a better frame. There is no ideal framing, but I believe you'll often end up with sort of a better understanding of the problem. Thank you.
Hey, thank you, Shalabh.